You may pause the video and try this by yourself first. So we have air and has mass of 76.0 grams. And what is a change in thermal energy? So we're doing thermochemistry here. And then it's from 15 degrees Celsius to -5 degrees Celsius. And specific heat for air is 1.012, and the units are joules per grams per degrees Celsius here. So temperature initial temperature is 15 degrees Celsius, but then temperature final is going to be -5.0 degrees Celsius. And we know that heat, or Q, energy, is equal to mass mc, specific heat, and then delta T. We have thermal energy. Mass of the air is 76.0 grams. And then specific heat for air is given. It's 1.012 joules per grams per degree Celsius. And then delta T is going to be final minus initial degrees, and this is degrees in Celsius. Let's cancel out the units here. Degrees cancel, grams cancel, and the units is in joules. And then put this all in the calculator here. So Q is going to be, it's going to be 1538.24 joules negative, but then it has to be in 3 sig fig here. So let's change to 3 sig fig. It's going to be -1540 joules. We know it's going to be negative because the air lost heat. It went from 15 degrees to -5 degrees. Let's do another problem. This problem, we're going to use water specific heat as over here. Why don't you give it a try first? Okay, so again, in thermochemistry, we got Q is equal to mc delta T. And mass of the water will be 2500 grams. And specific heat for water is going to be 4.184 joules per grams per degree Celsius. And then we got change in temperature. It's going to be temperature final minus temperature initial. But then we got the initial temperature to be 36.57. So let me put that. So it's going to be 36.57 and degrees Celsius. Every time you do this, you have to look at the unit for specific heat. You see how you got denominator degrees Celsius? That means you want the delta T to be degrees Celsius as well. And when you look at the problem, the Q value is given. It's 31380 joules. Okay, let's start canceling the units. Joules will cancel out. Grams will cancel out. C will cancel out. And T final is just going to be and we're going to get the T final here. Okay, now I'm going to divide these two terms since everything's multiplication everywhere. So let's divide 31380 divided by 2500, also divided by 4.184. That's going to equal to T final minus 36.57. And then all you do is I'm going to add 36.57 to the left side. So my T final is going to be in Celsius. It's going to be 39.57 degrees Celsius. That's the answer for this problem. Let's do another one. Okay, let's do this problem. I want you to try this first. So specific heat for silver is 0.233. Let me write that down. So C for silver is that. I'm going to hide this. Okay, let's see what we have. A sample of silver with mass. So mass, remember, look at the C. It's in grams, so I'm going to change it to grams. 11000 grams instead of kilogram. And the Q is going to be 60,000 joules. It says it releases, so it's going to be negative value. So initial temperature must be higher than 13 because as temperature goes down, the heat is released. So we got Q, negative 60,000 joules, is equal to mass 11000 grams. times specific heat 0.233 joules per grams over Celsius. And then it's going to be T final, which is 13.0 degrees, minus T initial. We don't know. Let's find that. And then that unit is degrees Celsius. Okay, so if we just find T final, it's in degrees Celsius. So again, just working with numbers, I'm going to divide these two terms. So it's going to be negative 60,000 divided by 11000, also divided by 0.233, and that's going to be 13.0 minus T initial. Or you could set this whole thing as delta T, and then solve for delta T, and then solve for Ti later. It's up to you. I'm just gonna do it this way. So if we divide, I got negative 23.4100 so on is equal to 13.0 minus T initial. Let me shrink this a little bit. Now if I add Ti to the left side, T initial is going to be 13.0 plus 23.4100 and so on. If you add the sig fig, must be the least precise, which is first decimal place here. So T initial is going to be 36.4 and degrees Celsius. So that's initial temperature, which makes sense because it used to be 36.4, but then now it got cooled to 13, which means energy got released. Let's do another one. This one too, I want you to try first. We got copper here, so that copper's specific heat is this one. And also water specific heat, liquid form is this. Okay, this time a hot copper sample is dropped into the cooler water. So imagine you got water here, it used to be water, but then copper piece, which is hot, got dropped there. So when equilibrium has reached, what would happen? The final temperature of both the copper, let's say that ball is copper, it should sink down, but you get the idea. Okay, so copper will release heat, correct? But then all the released heat will be absorbed by water. So their final temperature should be equal to each other. T final for water should equal to T final for copper. In the beginning, they're going to have their own TIs, initial temperature. Okay, let's see what's going on. So what this means is that Q, well, copper Q will be negative, right? Copper, because it's going to release heat. And then Q for water, it's going to be positive, correct? Because water will gain heat. But then the number-wise, it will be same. One's just negative, in this case copper, one's going to be positive. But in order to make them equal to each other, you need to put minus somewhere. It doesn't matter if you put it here, you put there. It doesn't really matter. Let's put it on the left side. So this is the concept here. Okay. So let me erase the drawing. So on the left side, I'm going to write Q for copper, and the right side, I'm going to write Q for water, and then set them equal to each other. So we got negative M copper mass, we don't know. That's what we're looking for. And then specific heat for copper is 0.385. This time I'm not gonna write the units here. I'm running out of space. And then delta T for copper, correct? Delta T for copper, what happens is that temperature of the sample decreases by 23. So delta T is actually negative 23.0. This time we're not given T final or T initial. They gave us the difference here. So that's going to be equal to M for water, which is 12 grams. Specific heat for water, it's going to be 4.184. And then this time delta T, what happened to the water here? The water temperature increased, so delta T is positive 8.0. And which makes sense. You get negative times negative will become positive. Mass is positive here. So mass is going to be 12 times 4.184 times 8.0 all over 0.385, and then 23 on the bottom here, 23.0. into sig fig, you're going to get 45 grams. So mass of the copper sample, it's 45 grams.